All right, next we are going to explore some laws. So let's talk about the law of conservation of mass in a chemical reaction. And the reason we want to talk about this, since we've been talking about the transformation of matter in a chemical reaction, we'll see that matter is transformed, but it's neither created nor destroyed in a chemical reaction. That happens only in nuclear reactions. Okay, that happens only in nuclear reaction. This is where changes in mass can occur. In a chemical reaction, there are no changes in mass. During physical and chemical changes, the total amount of matter remains constant, so as in chemical reactions. So for example, if I were to burn 58 grams of butane in a lighter, I'm going to need 208 grams for that of oxygen, a total 266 grams. As a result, I'm going to obtain 176 grams of carbon dioxide and 90 grams of water. If I were to add the reactant masses before and the product masses that occur after, you end up with the same amount of mass before and after. This is known as the law of conservation of mass. Let's take a look at another example. A chemist forms 16.6 grams of potassium iodide by combining 3.9 grams of potassium with 12.7 grams of iodine. Show that these results are consistent with the law of conservation of mass. All right, the solution would be, let's add them up. 3.9 plus 12.7 is 16.6. All right, so our reactant equal the amount of product we get. So this is consistent with the law of conservation of mass. You can look at example 3.15, and if you want to work out more problems, you go from 45 to 50. Now we come to the energy part of this chapter. Now that we've discussed matter and its classification and the changes it undergoes, if you recall, in chapter, I don't know if it was 1 or 2, chapter 1, when we talked about matter, or chemistry, we said that chemistry is the study of matter and the changes it undergoes, including energy. So energy is a major component of chemical reactions, in addition to being a great part of our universe. If we look at our universe is made out of matter and energy, regardless what type of matter and regardless what type of energy, right? That's beyond the scope of this class, but keep that in mind. It's matter and energy. So when we look at chemistry is the study of everything. Now, any changes in matter in a chemical reaction are driven by the desire for that's the wrong word. By matter seeking a lower energy state. Okay? Let me explain what that means. Let's say if you're on a ledge and your foot slips, you're going to fall to the ground. Why? Because that's a spontaneous, you're going to go to a lower energy state. Your position relative to the ground is changing. You're closer to the ground. That's a lower energy state. That's how all matter operate, a lower energy state. Now let's define what energy is. Energy is defined as the ability to do work. And the scientific definition of work is going to be when you push a substance, you're going to use a force. That force, if it actually works over a distance, we call it work. Okay, so it's a force acting on a distance. All right, the result of that force acting on a distance, we call that work. So energy is the ability to do work. Okay, so we go back to the potential energy of, let's say you're on 3 stories high and your phone slips out of your hand and it falls all the way down to the ground, to the street. It will break. Why? Because the potential energy that your phone had over that distance that it moved, it crushed the screen on your phone and it broke it. All right, so again, the behavior of matter is driven by energy. So we need to understand the fundamentals of energy in order for us to succeed in chemistry. Okay? The same like we said, matter is conserved, energy is conserved. And the law of conservation of energy states that energy is neither created nor destroyed in a chemical reaction. Let's be very careful. And when we say the total amount of energy is constant, we're referring to the energy of the universe. The change in energy in the energy of the universe is always zero. We don't gain nor lose energy in the universe. It's always zero. But that doesn't mean energy cannot be transformed or transferred. Okay? So energy can be transformed from one form into another, while energy can be transferred from one object to another. But energy cannot be created out of nothing, and it does not vanish into nothing. Let's be very careful. That is in a chemical reaction, because we all know that energy can be created out of nothing. Well, we can transform matter into energy in a nuclear reaction, and we can transform energy into matter in a fusion type reaction, whereas we can transform matter into energy in a fission type reaction. We get fusion happening in every star and sun. That's how we got our elements to begin with. All right. So the total energy of a sample is going to be the sum of its kinetic and potential. And let's be very careful with those. When we say kinetic energy, we're talking about energy associated with motion. And when we talk about energy that is potential, we're talking about the energy that is associated with composition or position. Okay? Let me tell you what the differences are. Again, when we go back to your phone, let's use a table rather than the third floor. If you pick up your phone from the ground and put it on the table, now it has a different amount of potential energy because its position has changed relative to the ground. When we talk about carbohydrates, we have carbon attached to another carbon, to another carbon, to another carbon. Let's take the simplest carbohydrate molecule, C6H12O6. Well, not the simplest, but rather the most common one that is used biologically, glucose, C6H12O6. We have 6 carbons attached to each other. Every carbon has an oxygen attached to it. And we have hydrogens attached to either a carbon or an oxygen. All carbon, oxygen, and carbon-carbon are single bonds except for one in glucose. When your digestive system, your central metabolic system in the cell, takes up a glucose molecule, it goes through glycolysis, citric acid cycle, oxidative phosphorylation, and at the end, you provide energy and you make ATP. Where does that energy come from? And if anyone has taught you before that energy is stored in bond, they're absolutely wrong. And it should never be thought of that way. The way we think of potential energy, we think of it as energy of position or composition. Okay, it's the position of carbon to oxygen. I have carbon with carbon and carbon with oxygen. When your body is done with that glucose molecule, it converts it into carbon dioxide and water. What we did is we went from carbon attached to carbon by a single bond and carbon attached to oxygen by a single bond In carbon dioxide, we have carbon attached to 2 oxygen molecules by a double bond. We change that composition. That change in composition leads to a lower energy state. That lower energy state is less taxing on your body or the universe. That extra energy is used to make water from oxygen and hydrogen. Once water is made, it releases a lot of energy. That energy is used to add phosphate into adenosine diphosphate to make adenosine triphosphate. All right, that's how it works. Notice how the total amount of energy is always the same, but it changes, it gets transformed. Now let me go through some of the types of other energies. The main 2 energy components that we need to look at are going to be where did that go? It's going to be, oops, wrong slide. It's going to be kinetic energy and potential energy. Okay, those are the 2 classes of energy. But we have subclasses. Electrical energy, which is the energy that is associated with the flow of electrons, which they have electrical charge. Okay, so anytime you have electron flowing, that's electricity. We call that electrical energy. So you can think of electrical energy as a form of kinetic energy. Thermal energy, on the other hand, is associated with the random motions of atoms or molecules, and that's also kinetic energy. Now, when we say chemical energy, that's potential. This is a form of potential energy associated with the position of the particle that compose a system. So let me tell you how transformation works. And we can use, you all drive. So let's use an internal combustion engine. You got yourself octane, gasoline in your gas tank. That's a form of chemical energy. When you hit the pedal, you inject that gasoline into the pistons in your internal combustion engine. What happens in there, the spark plug would allow the oxygen from the atmosphere to combine with octane. You give it enough energy to initiate the reaction. Then it burns. It gets converted into carbon dioxide and water. So now we've converted that chemical energy into heat. That burning releases a lot of heat. So it's converted into heat, thermal energy. Now that heat is going to cause your particles to move very rapidly. As a result, they push the pistons up. That pushing is used, that's known as mechanical energy. That mechanical energy or work is going to be used to cause the turning of the engine. It turns. That goes into your transmission, into the wheels, and now that movement, it causes the car to move forward. As the car moves forward, now we go into kinetic energy, right? That movement, that kinetic energy. Then you keep going with that kinetic energy. Someone texts you, you pick up your phone, you want to text them back. You don't realize that the car in front of you just suddenly stopped, and boom, you hit them in the back. Now you have converted that kinetic energy into work and heat. That's that work, that kinetic energy is what causes the damage to your car and the car in front of you. That's how usually energy gets transferred and transformed. And the units we use for energy, the SI unit is joule. Okay, joule is the SI unit. And the definition of that is going to be the amount of energy that is required to move 1 kilogram object a distance of 1 meter. All right, so joule is the unit for work, is the amount of energy that is required to move 1 kilogram object a distance of 1 meter. Calorie, on the other hand, is defined as the amount of heat that is required to raise the temperature of 1 gram of water by 1 degree Celsius. That calorie, lowercase right here, is completely different than a nutritional calorie, where uppercase C is used. So it's written as uppercase C cal, which is equivalent to 1,000 kilocalorie. I'm not going to go into why that is, but you should be able to figure out. They manipulate us left and right. So the kilowatt hour is 1 kilojoule per second time. Okay, since there are 3,600 seconds in an hour. Okay, so you multiply it by this, you get kilowatt hour. 1 kilojoule multiplied by 3,600 seconds, you get kilowatt hour. These are, excuse me, the conversions between all that I gave you. The most important one that you need to memorize will be the following. You should memorize this one. 1 calorie is 4.184 joule. I hope I made it clear enough by keep highlighting it. All right, there you go. All right, let's take a look at an example. A candy bar contains 225 uppercase calorie. That means this is a food calorie of nutritional energy. How many joules does it contain? All right, so I have 225 uppercase calorie, and I want it in joules. So I'm going to go from food calorie to scientific calorie. So I'm going to use the relationship I just shared with you in this table, 3.2. Then I can convert from calorie to joule. 1 calorie is equivalent to 4.184 joules. That's the conversion factor. So I go from 225 food calorie, convert to scientific calorie. That would be 1,000 scientific calorie per 1 food calorie. Then to go from scientific calorie to joules, I'm going to use the following conversion factor, 4.184 joules in 1 calorie. I cancel food calorie with food calorie. Scientific calorie with scientific calorie, we end up with 9.41 times 10 to the 5 joules. All right. Another example would be 3.16, and these are all the problems you can work with. Potential energy, I already told you about potential energy and heat. And now, how do we relate that energy to chemical reaction? All right, so let me just skip here and go over here. The way we're going to look at it is as follows. We arbitrarily, since energy was a term that was invented by human, so we don't have an absolute energy of anything. We always put an arbitrary energy scale and say relatively what are the energy states between two things. In this case, reactant and product. That's what we're interested in chemistry. Reactant and products. So if the energy of the product is lower than that of the reactant, then energy is going to be released. We call that an exothermic reaction. If the energy of the product is greater than that of the reactant, we call it an endothermic reaction. All right? In an exothermic reaction, energy is released and it has a negative sign because it's lost by the system. Whereas in an endothermic reaction, energy is gained and we have a positive sign for energy in here. As we discussed earlier, thermal energy is the constant random motion of matter. So we know that atoms and molecules that make up matter, regardless if it's in the gaseous state, liquid state, or the solid state, particles are moving. Whether they're vibrating or actually moving freely, it doesn't matter. They have some kind of energy. We call that thermal energy. Now, let me assure you, when particles have zero energy, matter does not exist. One of the conditions of matter to exist, it must have kinetic energy. Matter, positive, must have positive energy. So that thermal energy can be measured by using temperature. Okay, so that temperature is a measure of its thermal energy. The hotter the object, the higher the temperature, and the greater the thermal energy. That means the faster the particles are moving. That's the way we want to think of it. Heat, on the other hand, which has units of energy, same as work, is going to be the transfer or exchange of thermal energy caused by temperature difference. Let's be very careful with this. All right? So for example, if you're on a warm day and you would like a cold drink, but you bought the bottle and let's say you have a soda and it's really hot, you want to make it cold, what do? You get some ice, you drop your ice in your cup, and all of a sudden it becomes desirable to drink. Why? Because water was hotter than ice, so you get a transfer of heat from water to the ice, causing it to melt. As a result, water will lose heat to increase the temperature of the ice. So let's say the cubes of ice you got were like minus 20 degrees Celsius. They will increase until they get to zero. At zero, they'll start melting. That's how you transfer thermal energy. Let's be very careful. Heat is not temperature, and temperature is not heat. Temperature is a measure of the thermal energy of matter, not the exchange of thermal energy. I hope that is clear enough. We measure that thermal exchange by taking the temperature. And they have completely different units. The units for heat is either joule or calorie. The unit for temperature is going to be either Fahrenheit, Celsius, or Kelvin. Now, everyone is familiar with the Fahrenheit scale. Unfortunately, it's scientifically speaking, it's a useless scale because it was based on the freezing point of concentrated saltwater solution and the body temperature, the normal body temperature of a human. So it's really bizarre. 0 degrees Celsius, and whereas the Celsius scale is based on pure water. So water freezes at 0 degrees Celsius and it boils at 100 degrees Celsius. Now, because water, that scale took water into account, and we can definitely take water lower than 0, then it's not scientifically sound. Remember what I said? Matter cannot have 0 kinetic energy. That means temperature cannot be 0, let alone be negative. Therefore, the Celsius scale is not useful scientifically either. We needed a better scale, and that would be the Kelvin scale, where we have an absolute 0, where matter cannot exist at that temperature. It doesn't exist. But it's still based on boiling and freezing point of water. So water boils at 273 K, and it boils at 373 K, and it freezes at 273. So you have 100 Kelvin per 100 Celsius degree. That's an easy conversion between the two. But Fahrenheit, we have to come up with a clever way. Now, I'm not going to go over how we arrive at that. I'll just tell you directly. Notice right here, 100 versus 180. That means every 1 degree Celsius is equivalent to 1.8 degree Fahrenheit. With me? Then in addition, the starting point for Celsius is 0, but the starting point for Fahrenheit is 32. That means we need to add 32 to it. With Kelvin, it's 1 degree Celsius, it's 1 Kelvin. Notice that for Kelvin, we don't use degrees. We do that for Celsius and Fahrenheit. I can't stress that enough. Please don't use degrees for Kelvin. Please, please, please. Since the starting point is not 0, we need to add 273 on top of the Celsius to get to Kelvin. So we can come up with the following conversions. Kelvin is degrees Celsius plus 273. For Fahrenheit, let me write it differently than it is written. It's given to you in your textbook. I would rather have it as follow. temperature in degree Fahrenheit equals 1.8 degrees Celsius, or temperature in degrees Celsius, plus 32. All right? And if you're looking to go from Celsius to Fahrenheit, you're going to use this one. If you're looking to go from Fahrenheit to Celsius, you're going to use this one. And if you want to go from Kelvin to Fahrenheit, then you can convert from Kelvin to Celsius, then Celsius to Fahrenheit. All right, let's take a look at a few examples. Convert negative 25 degrees Celsius to Kelvin. I'm given negative 25 degree. I want to convert it to Kelvin. So I want to go from Celsius to Kelvin. I'm going to use the following equality. All right. So Kelvin is going to be negative 25 degrees Celsius plus 273.15 equals 248 K. You got some more practice problems you can work with. Let's do Fahrenheit to Celsius. Convert 55 degree Fahrenheit to Celsius. So I want to go from Fahrenheit to Celsius. I'm going to use the following equality. 55 minus 32 over 1.8 will give me 12.778 degrees Celsius. Now, when it comes to sig figs in temperatures, if the given temperature to you have any decimal places, your answer should have the same number of decimal places. We don't worry about sig figs, we worry about decimal points. 55 has no decimal places, my answer should have no decimal places, so it's 13 degrees. These are some more practice problems you can look at. Let's take a look at converting Kelvin to Fahrenheit. 310 to Fahrenheit. So I'm going to go from Kelvin to Celsius, then Celsius to Fahrenheit. Okay, so if I want to convert from Kelvin to Celsius, I'm going to rearrange this equation to be Kelvin minus 273.15. That'll be 310 minus 273.5 will be 36.85. Keep in mind, no decimal places, right? 310, no decimal places. Then I want to go from Celsius to Fahrenheit. I need to rearrange this the same way I rearranged it for you earlier. That would be Fahrenheit equals 1.8 degrees Celsius plus 32. So you plug in the values, 1.8. I bring in this down here, 36.85 plus 32. I get 98.33 degrees, which is 98 degree Fahrenheit. For more practice, you can take a look at these. Now, the last part of this chapter, we are going to look at how do we actually measure the heat transfer between things. How can we use temperature to figure out how much heat has actually been transferred? In order for us to get that, we need three factors. In order for us to measure this, we need to know how much of that substance we have. We need to figure out how much the temperature has changed. And we need to figure out what's the ability of the substance we're looking at to resist any addition of heat before its temperature changes. We're going to call that last one specific heat capacity, which means the ability of the substance to absorb heat without immediately changing its temperature. And if you notice this list, it's given to us in joules per gram per degree Celsius. In other words, it says the amount of heat I add to it per gram of the substance per degree Celsius. That's what this is. The ability to resist the amount of heat you're given per amount of substance per change in temperature. And if you look at this table, you'll notice that water has the highest heat capacity. All right? And it is so. That's why water is, for example, is suitable for life. Okay? That's one of the many reasons why water is. It helps us maintain homeostasis. Water is actually wonderful if you live In a beach community, you know that the weather is always much cooler than inland because water has a higher heat capacity. So the air particles will actually interact with the water. They lose that heat. So when we feel heat during the day, that heat is actually because the gaseous particles in our atmosphere are hot. But when they hit water, they cool down. So that's what happens. Now make sure you use that table. I don't expect you to memorize any of these things. But if you remember, for water, that was the definition of calorie, right? How much it takes energy to raise the temperature of water, 1 gram of water by 1 degree Celsius. That was the specific heat capacity. All right, that's the calorie. So we can relate all of these quantities by the following equation. So the amount of heat, that internal energy transfer that we were talking about, we're going to give it a symbol Q, equals the mass of the substance times the specific heat capacity times the change in temperature. We're going to use the following symbolism. M for mass, C for specific heat capacity, and delta T for temperature change. The units for Q is going to be joules. For mass is going to be gram. For delta T is going to be degrees Celsius or Kelvin. It depends on what we're given. We can use either as long as they're consistent with the units of the specific heat capacity. So the units for the specific heat capacity are going to be joules per gram per degree Celsius. And if you look at it, they should all cancel out and give us joule. That doesn't mean we should only use this equation to calculate Q. We can rearrange it to calculate any one of these 4 quantities that usually will be given 3, and we need to figure out the 4th. Let's take a look at an example. Gallium is a solid at 25 degrees Celsius and melts at 29.9 degrees Celsius. Okay? If you hold gallium in your hand, it can melt from your body heat. How much heat must 2.5 grams of gallium absorb from your hand to raise its temperature from 25 to 29.9, and the specific heat capacity of gallium is 0.372 joule per gram per degree Celsius. All right, few things before we start on this. We need to notice that the question is asking for how much heat it requires to raise its temperature to its melting point. We don't want to melt it. We don't want to calculate how much heat is required to melt it. That's beyond the scope of this chapter. We're going to come back and learn about it when we get to chapter 12. There is a way to calculate that, but not for this chapter. So we need that. Now let's take a look at the information we're given. Let's actually gather that in one place. We're given the mass of gallium, we're given initial temperature, final temperature, and the specific heat capacity, and we're looking to find Q. So what I want to do, I have C, M, and delta T, and I want to find Q. Easy peasy, right? We need to make sure we got the right units, everything matches, and we should be good to go. I have C, I have mass, and I have delta T, which is T final minus T initial, 29.9 degrees Celsius minus 25 will give me 4.9. Notice I have 1 decimal point, 1 decimal point. My answer should have 1 decimal point. MC delta T, 2.5 grams of gallium times its specific heat capacity. It's joule right here, not 1. 4.9 degrees Celsius equals 4.557 joules. Now keep in mind, this is the amount of heat it takes to raise its temperature only. We are not talking about melting it. Melting it requires an additional maybe 200 joules that is needed to melt this. We are not going to look at it until chapter 12. But for now, this is it.